All right, kids, here we go. So where we're at right now is that we have covered what's called the rate law, okay? Now, technically, and that was that process that you all just did where you did the cancellations, and what you end up with is the full-blown technical name of this thing is that what you all just did is technically known as the differential rate law. And what happens here is, and this is what you all came up with on that assignment, you have zero order R equals K, first order R equals K times concentration of A squared. And again, don't forget with that A squared, that could be also K times, hold on, I use my highlighter. Let me back up the bus. That could also be K times like the concentration of the magnesium ions times the concentration of chloride ions. And that's another thing I want to get out of your minds right now, that this is always just going to be in terms of A. This is actually going to be in terms of some chemical. We just always use A as kind of like the basis of the explanation. So usually when you talk about this, usually you leave out the word differential. So if I say, hey, write the rate law, this is what you're talking about. But what you'll notice on the rate law is that there's no value of time. So your rate is only dependent upon the concentrations, unless it's zero order when it's only dependent upon the rate constant. So, quick reminder, when you come down here and you look at these units, and this is what we came up with yesterday, that any rate has to end up in molarity per second. So this is why if it's a zero order, you have units of molarity per second. If it's first order, it's 1/seconds, because if you multiply molarity by 1/seconds, you get molarity per second, which is what that rate is in. If it's a second order, it's m to the -1, s to the -1. You could write it as 1/molarity seconds. Again, I don't care, just pick one. So what we're going to cover today is, and I know you all are just giddy with excitement, is the integrated rate law. Now, what's going to be odd about this is that all of these are going to be linear functions. Even though it looks completely jacked up, all of these are y equals mx plus b. Now, I've got zero order on here, but like on the assignment, we won't have anything that's zero order. So it's there. We're going to talk about it in terms of half-life when we get into it, but it's generally not on the AP exam, because if you look at what you have on your equation sheet, they don't even have like zero order listed as on the equation sheet. So what you're going to focus on much more is going to be first order and second order equations. So here's the most important part. Because these are linear, we're going to look at what you can graph that will show up as a linear function. So what's going to happen here is that, for example, first order and second order, because this is what we're going to spend most of our time on. So if it's first order, if you look at this natural log of A versus kt times natural log of A naught. So this is just right here, this is just your y value. So what's going to be important is that we're going to graph natural log on the y-axis, and we're going to graph time on the x-axis. If it's second order, when you graph the inverse function of A versus time, that's what produces a linear function. So what you'll see is when you graph these, if it's a first order, you have a negative sloping line. If you have a second order, you're going to have a positive sloping line. So that's all that negative sign is indicating, is the sign of the slope. Don't worry for now about half-lives. We'll get into those on the next lecture. So we'll get into that. Don't worry about it for now. But all the half-life tells you is how long it's going to take some initial concentration of A to become half of what it was. So if you start with an initial concentration of 0.5, how long does that concentration take to drop to 0.25? For now, don't worry about half-lives. We'll get into that later. So when you're going to look at this, and this is what we're going to focus on down here, is that's going to be these units of k. So if it's first order, it's going to have units of 1 over seconds. If it's second order, it's going to be 1 over molarity seconds. So here's how these problems typically play out. So since I know that it's 1 over a versus time is what's my linear function, now I know that how I'm going to express this. So what I'm going to do, and I'm going to go back here, hold on. Okay. On your equation sheet, they don't tell you that this is first order. They just give you this generic equation. So here's how I always remember it. Natural log looks like a 1. So I always remember that natural log is first order because a 1 looks like an L. I don't care how you remember it, just find a way to remember it. Okay? I don't care. Just find a way to remember it. So, but remember, if you have to undo a natural log, for those of you that are math nerds, okay, let's hit it for the math nerds, then to undo a natural log, you have to have that E function to undo that natural log. And so I'm going to work a problem. Now, I'm going to stop this for a second because it's easier if I upload 2 lectures instead of 1 big lecture. So we'll return after a quick message from our sponsors. Okay, so here we go again. And we're going to come in here and see if this math actually... The integrated rate law, now because I do deal with values of time, then I can know what that concentration is going to be as a function of time. Or if what we'll get into tomorrow and say, hey, I want to figure out how long it takes for a concentration to drop to a certain point. Okay, so if I know I'm starting with a concentration of 0.1, and I want to know how long it's going to take for that reaction to go until it becomes 0.005 or whatever that is, then all I'd have to do is solve for that value of time. So the integrated rate law is a much broader tool to calculate concentrations as a function of time. If you look at a first order in terms of just your rate law, and this is what you all did on the assignment from yesterday. Notice that time isn't here, okay? This is going to be the big thing. There is no value of time. But you end up with these units, and again, oddly enough, you've been my students long enough. This has units of 1 over seconds. This has units of 1 over molarity seconds. If there's ever a section that you pay attention to the units, I beg of you, pay attention to the units on this. That's going to be huge. Okay? So, how this... Again. Your rate law doesn't allow you to calculate a concentration at a point in time. All that's going to say is, hey, what's this initial rate of this reaction going to be? So I can't do anything with time. But so it plays out. What's going to happen is that you're going to be given a table of times and concentrations. So this is a simple decomposition reaction. A is going to decompose into B and C. Okay? That's all you got. It's a simple reaction. It could be ozone decomposing into oxygen. Okay? Could be magnesium chloride decomposing into magnesium and chloride. It doesn't make any difference. Okay? So, and again, there is no shortcut way to do this. There is no shortcut way. So the first thing that you have to do, and I've already done this to save us some time, is that you've got to take these concentrations and you've got to take the natural log of those concentrations. So if you take the natural log of 0.01, you get negative 4.605. You take the negative log of 0.00787, you're going to get this value. The other thing that you're going to have to do is then you're going to have to take the inverse of A, okay, which if you take the inverse of 0.01, you get 100. If you take the inverse of 0.0787, you get 127. There's no shortcut way to do this, okay? Listen to me. There's no shortcut way. So when you're given these values of time, the first thing that you have to do is take the natural log of the numbers and then the inverse of those numbers. That's it. There's no shortcut way to do this. So here's what's going to be huge. Pay attention to this in terms of the scale. So notice here you went 0, 50, 100, 200, 300. So when on a lot of times what they'll do, like on the scale, they might change the units, okay, and go, hey, 0, 50, 100, 200, 300, okay? Then over here, notice that this concentration of A is dropping as a function of time, okay? You started at 0.01, then it's going to become smaller and smaller and smaller and smaller and smaller. So once you know what these values are, and you can look at this in terms of a trend. So what we would do is we would somehow measure the concentrations of these as a function of time. And then once you get those, then you're going to take the natural log and then the inverse of those. That's just the first thing that you've got to do. Now, based upon that data was 0.01. So when I take the inverse of that, if I want to find that concentration at 25 seconds, I know that that concentration has to be somewhere between 0.01 and 0.00787. So when I find that concentration at 25 seconds, I know it has to be somewhere between these 2 points. If it isn't between these 2 points at 25 seconds, then I've done something wrong, okay? So that's going to be the whole key to this thing. Now, if it was first order, and what's on your equation sheet, if I'm going to back up. So we at 25 seconds, that matches where we said this was going to be, because we said it had to be somewhere between 0.01 and 0.00787. And then we got, if the old man remembers, 879, which fits in this gap. So the math holds, life is good. So here's the main difference between the rate law and the integrated rate law. The rate law, if you go back to, here's what we've got. Next thing. I went ahead and drew this. So what I did on this graph is that here's my time scale, okay, along the bottom. And then what I did is that, and this is a handy technique. Some people like this, it flips other people out. I don't care. If you're good with this, hey, go with it. So what you can do is you can keep the same time scale, and then come in here and go, okay, hey, I'm going to graph the natural log of A on this y-axis. Then, to save time, I came over here and then I graphed the inverse of A on this axis over here. So if this is going to flip you out, just do 2 different graphs, okay? You don't have to do this. I did it this way just to kind of save some space because of the fact that I didn't want to have to go through and draw 2 different graphs and scan it and put everything back into this thing. So this is why I put these on the same axis. If you want to do this, great. If not, not a big deal. Now, here's what's important. Over here on this natural log of A, okay, here's what's going to be important. Once you take the natural log of something, there are no units, okay? There are no units. So this side over here has nothing. Now, when you take the inverse of the concentration, then you're going to get the units of 1 over molarity. Okay? Now, that's a hideous color of yellow. Okay. I don't like that. Let's go with this. All right. So that's going to be 1 over molarity. So once you get this drawn, what you're going to do is you're going to look at these, and typically, one of these is going to show up to be pretty linear, like this, okay? And the other one, one's going to show up being nonlinear, which is this natural log of A. And then the one that is linear it would be pretty self-evident. Sometimes you kind of have to pick the one that's most linear. That doesn't happen very often, but sometimes when you actually deal with data from a lab, you kind of have to say, well, which one is the most linear, okay? Usually there's a pretty clear-cut differentiation between the two. So here's what's going to be important. Now that I know which one is linear, what I did is that I came in here and I found the slope. So I circled the points that I was going to use, okay, 200 seconds and then 210. So when you find this slope, notice that that is 1 over molarity, and then 1 over molarity, and then divided by seconds. So the units that I'm going to get out of that are 1 over molarity seconds. So this is this value of K. So at this point, I have found K. So what's going to happen, go back, my K value is 0.55. So I know my initial concentration. So if I come back here, this thing was second to our data, is that when I look at this in terms of the graph, because of the fact that I know that 1 over A is what's going to be the linear function. So if you go, I'm going to, hold on, don't flip out, I'm going to go back and say, okay, hey, this thing is second order. So I know that 1 over, let me back up. So I know that 1 over A is going to equal my value of K, which in this case, 1 over molarity seconds times time plus 1 over A naught. So this is Y equals mx plus b. So this is what makes this thing a linear function. So this is my slope. Now, this is where the magic happens. So if you look at this in terms of slope, this has units of 1 over molarity. This has units of 1 over molarity. I take 1 over molarity seconds, and I multiply that by seconds. The seconds cancel out. I end up with 1 over molarity. So now everything has the same units. So what's going to happen is that once you know this equation, you can plug in a value of time. So in this case, I've got 1 over A naught. So my initial concentration, hold on, stay with me here, I got to back up. So then I'm going to have 1 over 0.01, which is going to be 100, okay? So now I know what my y-intercept is. I know my slope. T is what's graphed on the x-axis. This is going to get me that value of y. So as jacked up as it is, all this is saying, oh, okay, here's my value of K, which is your slope. Here's your values of time. That's what goes on that x-axis. And here's your y-intercept. Here's going to be your values of y. So now, and this is the beauty of the integrated rate law, is that now if I know what that value of time is, now I can say, okay, hey, I want to know what the concentration is after 25 seconds. So I can plug in 25 seconds, multiply that by 0.55, add that to 100. Now, here's what you have to look at. When you actually get this concentration of A, this is like the inverse of A, so you've got to like flip it over. So here's the beauty of having this data. If I want to figure out the actual value of the concentration of 25 seconds, this is where you want to be able to use your data set. So we're going to come in here and go, okay, go back. So 1 over A is going to equal 0.55, 1 over molarity seconds. And we said we're going to pick a time of 25 seconds plus 100. So if you do the math, you take 25 times 0.55 and add that to 100, you get, wait for it, 113.75 equals 1 over A. So then if you take the inverse of this, then you get A equaling 0.00879. Okay? Now, then You remember this number, 0.00879. So now, in your assignment, there's going to be 4 problems. If you look on your assignment, you're going to have, the first sheet is going to have all the numbers, and you're going to have to do the calculations, and I'm going to scan that, and I'm going to give you that data so you can see what that looks like. You're also going to have a scanned sheet, and there's going to be 2 problems on that, 29 and 31. So I'm going to give you the answer key to the ones that is due here, that's actually on this. These 2, 29 and 31, those are due on Friday. You're going to get this on Wednesday. These are going to be due on Friday. So I want 2 graphs for both of these. So you're going to have a natural log versus time, and you're going to have an inverse concentration versus time. No pun intended, take your time on these graphs. And if you want to do them like I did, where you combine them both on the same axis, hey, that's great. If that's going to flip you out and you want to draw them as different graphs, that's fine. So on the packet of the scanned stuff, you're going to have a sheet of graph paper. So if you want to print that out, if you want to use your own graph paper, that's fine. I just included that so you had that available. So here we go, kids. Integrated rate law. That's all we got. Stay safe and be good.